Alright, we've spent a whole semester talking about limits and derivatives, and now we're going to shift focus a little bit. We know that derivatives look at instantaneous rates of change for a function, but what happens to those changes when they accumulate over time? Well, if we have this function f of x, we know the derivative is the rate of change, but what we're going to discover is that the accumulation of all those rates of change is the area under the curve. Now, this is integral calculus. We've been doing differential calculus with derivatives, and now we're going to do integral calculus and look at that, those areas under the curves and what that means. So, this is section 5.1 in your book. You want to definitely read that. Let's look at an example here. If we have a car traveling along at 50 miles an hour, and we know they travel for 2 hours, then if this is our velocity function here, it's a constant, 50 miles an hour. We know that distance equals rate times time. So our distance is going to be our velocity, 50 miles per hour, times our time, 2 hours, which means we traveled 100 miles. But if you look at the graph, notice the area under this curve from 0 to 2, what is it? Well, this is a rectangle, and we know that a rectangle is length times width to find its area. So its length is 50 and its width is 2. So 50 times 2. So the area under this curve along this space gives us its distance, its total distance. Now, what did we talk about with position and velocity? We said that velocity was the derivative of position, which means that position is the antiderivative. Remember, we looked at that a little bit. The antiderivative of the velocity. We're going to use those antiderivatives to find these areas under the curve, because those antiderivatives tell us about the area under the curve, which tells us that accumulated rate of change. How much we had this rate of change of distance. We were changing our distance. How much did it accumulate over the 2 hours that we're talking about? So it looks easy when you do it with a little rectangle and a constant, but what happens when you have a more complicated function? What if our velocity function is a parabola? And we still want to know what happens for the first 2 hours. What's the accumulated rate of change? The distance that we went in that 2 hours, if this is our velocity function. It's still going to be the area under the curve. It's a little more complicated to figure out because we don't have a nice geometric shape that we know how to find the area of. So what we're going to do is to start with at least, we're going to do something called the rectangular approximation method, or RAM. And what that does is it uses those geometric shapes that we know and helps us to find the area. So if this, draw a bigger picture here. If this is 2, and this is our velocity function, v of t equals t squared, what we can do is we can use rectangles, and for example, we can use 2 rectangles here and use a midpoint for their height. We'll have a rectangle here, and then another rectangle here. And this can approximate our area. Now this would be an MRAM is what we would call this, because we use the midpoint to find our height for the rectangles. Now we know how to find the area of a rectangle, length times width. So this would be the function value at 1/2, so this would be 1/2 squared, or 1/4 would be our height for this rectangle, and our width would be 1. And here we'd have 3 halves, squared. That'd be our height, because that's the function value at this x value, the midpoint between these two. And that would be our height, and we'd have our length. Now, you can also use your left hand. If we're only going to do 2, if we do our left hand for our height, then this rectangle is not going to have much. And this rectangle here is going to be really short. And we'll use our height. We use our height here, and that would be an LRAM. We use our left hand where we hit the curve, left hand approximation. And then, of course, we can also use a right hand approximation. So if we want to use this two rectangles, the right hand side of this space would be here, so we'd have a rectangle up here, and the right hand here would be here, and that would be an RRAM. And those are the 3 different RAM approximations that we're going to use for rectangles. Now, if you look at this picture, it's pretty clear. If you use more rectangles, you're going to get a better approximation. Now, calculating this out by hand is very tedious, especially if you start using a whole bunch of rectangles. To do the RRAM here, all we have to do is say, well, the height here is 1, because that's what 1 squared is, times 1. So we've got our first rectangle has an area of 1, and our second rectangle has an area where the height is 4, because that's 2 squared, times 1, which is our width of the rectangle. So we just calculated out. It's pretty easy with 2 rectangles, but it's also not very accurate, because we want this area here. And the red rectangles way overestimate it. The blue rectangles way underestimate it. The midpoint ones are pretty good, because we've got this part out of it that kind of makes up for the part that's still in it. So the midpoint one might be a little bit more accurate. But with more rectangles, we're going to get more accurate, and it's going to get more tedious. So what I'm going to do is I'm going to give you a program for your calculator that will help you calculate this out. So let's see if we can get this thing to work today. So on your calculator, I'll give you the program, and I'll give it to you in print form so you can type it in, and we can also do the link up so that you can get it a little bit easier. But what you do is first you go to your y equals and put whatever your function is in. So we have x squared is our function that we're looking at. And then once you've got the program in your calculator, you'll type, go to program, and you're going to execute the RAM program. So we hit enter, and A is the left-hand spot. So that's 0. We're going from, here you can see we're going from 0 to 2. Sorry. See if we can get everything out of the way here. There we go. All right, so from 0 to 2, and then the number of sub-intervals. That's how many rectangles do we want? Let's try it with 10 rectangles, because 10 rectangles would give us a pretty good idea. Then you hit enter, and it'll tell you what the area is with a left-hand approximation, a midpoint approximation, and a right-hand approximation for the height. Okay, so here you can see they're all pretty different. 2.28 from the left and 3.08 from the right. As we looked at with this graph, the right is overestimating, the left is underestimating. That's not true for every graph, so make sure you kind of look at your sketch and see which is going to be better. And then the midpoint's right in the middle. Now, if we want to use more rectangles, again, we're going from 0 to 2. Let's say we use 100 rectangles. Takes it a second to calculate it while this freaks out. And you can see that we're much closer together at this point because we're using more rectangles. That's less space that's not actually part of the parabola. So the main point of this is finding your area. We're approximating area under the curve, which tells us accumulated rates of change, so that we can figure out what this area is with rectangles. Now we're going to get more and more accurate with our technique with different ways to do this, but for now, right now, we're looking at rectangles under the curve, and that's RAM. We'll look at MRAM, LRAM, and RRAM for our rectangles, and we'll use the calculator program to do that. You do need to know how to do it by hand, but as I said, calculating area of a rectangle, that's pretty basic elementary school stuff, so I figure you guys can handle that, and it does get really tedious when you have a lot of rectangles. So look at that. One thing you want to look at is the cardiac output example in your book. It'll show you a little bit more practical application of this. We'll also have another video for this section that'll deal with spheres.